Okay, so here we have two 1 kilogram masses on a frictionless table, 1 meter apart, center to center. Now, the first thing we're going to do here is find the magnitude that one of these forces has on the other, for which we are going to use Coulomb's law. The charge on both of these is 10 microcoulombs, which is, a microcoulomb is 10 to the negative 6 coulombs. So we're just going to plug this in. So we have K, whoops. Let's write F first. Okay, so the force equals K, which K equals 9 times 10 to the 9th. It is a constant. So we have that times the charge of the first one, the first particle, which is plus 10 times 10 to the negative 6, because it is a microcoulomb. And then, sorry for leaving off the units here, times the charge of the second one, which is another plus 10 times 10 to the negative 6. And that is all over the distance between the two, which is 1. So that's 1 squared, which is 1. So running this calculation ends up getting you that the magnitude of the force that one of these has on the other is 0.9 newtons. Okay, so that is the first part of this. The second part is asking what acceleration would one of these have on the other if it were to be released. So if we remember that force equals mass times acceleration, or as we did in 131, acceleration equals force divided by mass, which is more useful. We're going to go ahead and use this, and we already have the force, and it's the same on both of them, so it doesn't matter which one we choose. So the acceleration on one of these particles equals 0.9 newtons over the mass, which is 1 kilogram. So the acceleration that one of these particles, the charge one of these particles imparts on the other, ends up being, well, 0.9 meters per second squared. So that's just a basic run-of-the-mill Coulomb's law problem. And that's it.
All right.